In this recording I'm going to look at the properties of the angular momentum shift operators and form the matrix representations for the x and the y angular momentum operators. We've looked at the properties of the Lz operator, which when applied to an angular momentum eigenstate generates the eigenstate back again. That means the state is an eigenstate of the angular momentum operator Lz multiplied by the number h bar ml. And similarly for the total square angular momentum operator L squared, for which the state LML is also an eigenstate, and which generates then the same state back again, but this time multiplied by the eigenvalue h bar squared times L plus 1. Now the shift operators are composed from the x and the y angular momentum operators as follows. The raising operator is given by the operator Lx plus I times Ly, while the lowering operator is given by Lx minus I Ly. And it turns out to be convenient to look at the properties of these raising and lowering operators first before we get onto the properties of Lx and Ly. Now you see from these formulae that if we just add together the raising and lowering operator, we can just add the right hand sides of this equation together. The Ly terms cancel out when we add those two equations together, so we get 2Lx, and hence we can deduce that Lx is a half of the sum of the two shift operators. Similarly, if we take the difference between the two shift operators, we just subtract these two equations, then this time the Lx terms cancel out and I'm left with 2I Ly. So I can then deduce that Ly is given by 1 over 2I times L plus minus L minus. So it's possible to go back and forward between the two shift operators L plus and L minus and the x and y operators using this system of equations. In fact, the system of equations is very similar to the mathematics of complex numbers. So if I define a complex number in terms of two real numbers, a and b, so the real part of z is the number a and the imaginary part of z is the number b, a and b both being real, then I can define the complex conjugate of z by changing the sign of the imaginary part as follows. And if I add together the complex number with its complex conjugate and divide by 2, then I get the real part. And if I subtract the complex conjugate of the complex number from the complex number and then divide by 1 over 2i, then I get the imaginary part. So you can see that there's a close analogy between the shift operators L plus and L minus and complex number and its complex conjugate. One can add the L plus and L minus operators, divide by 2 to get the x operator. Similarly, one can add a complex number to its complex conjugate and divide by 2 to get the real part of the complex number. If one subtracts L minus from the L plus operator and divide by 2i, one gets the Ly operator. Similarly, if one subtracts the complex conjugate from the complex number and divide by 2i, one gets the imaginary part of the complex number. So now we're going to look at the properties of these raising and lowering operators, and then we're going to come back again and construct, using these equations, the matrices for the Lx and the Ly operators. So let's look first of all at the raising operator, L plus. So if L plus is applied to one of the angular momentum eigenstates, the result is not the same eigenstate. This operator generates a state in which the ml value has been increased by 1, and that's why it's called a raising operator, and it multiplies that by some complicated factor which we'll look at in a minute. But the main point to concentrate on right now is that when L plus, the raising operator, is applied to the state LML, we get the state LML plus 1. So the angular momentum quantum number ml has been raised by 1 unit. So for example, if we have the set of states with L equals 2, so we would have 5 states denoted 2 plus 2, 2 plus 1, 2 0, 2 minus 1 and 2 minus 2, then the L plus operator, if applied to the state 2 minus 2, generates the state 2 minus 1. If it's applied to 2 minus 1, we get 2 0 and so on. So the L plus operator can be used to walk between these states. Similarly, the L minus operator, the lowering operator, when applied to the state ket L ml, generates the state ket L ml minus 1. So with the ml quantum number lowered by 1. And again, this is multiplied by a complicated factor. So overlooking that for the time being, the L minus operator takes the state 2 plus 2 and lowers the ml quantum number to get the state 1 below. So these operators, L plus and L minus, walk up and down the ladder of states with the same value of L, but different values of ml. And let's look at this now in more detail. We'll answer the question of what happens if we apply the raising operator L plus to the state which has already been raised as much as it can. So the state 2 plus 2, there's no value of ml larger than plus 2 belonging to the state L is 2. So we'll answer the question, what happens if L plus is applied to the top state? And similarly, what happens if L minus is applied to the bottom state? So for this we have to look at those complicated factors. So for L plus, the complicated factor is given by h bar times a term which looks like this: L times L plus 1 minus ml plus 1 square rooted, and the new state appears with ml raised by 1. Now the terms in this are recognizable. The number L times L plus 1, that was the eigenvalue of L squared. We can see we subtract a term which is ml, the old quantum number ml, multiplied by ml plus 1. That's the new quantum number after it's been raised. So let's see some examples. If we apply L plus to the state ket 2, so the L equals 2 state with ml is plus 1, and we just plug in those numbers, we have 2 times 2 plus 1 minus the quantum number ml, which in this case is plus 1, multiplied by the quantum number raised by 1, because we're looking at the raising operator, so that would be plus 2. Close the brackets, take the square root, and write the new state with the ml value raised by 1, which gives the state plus 2. And we can evaluate that. The first term evaluates to 2 times 3 is 6. The second term evaluates as 1 times 2 is 2. So I have 6 minus 2 is 4, square rooted, multiplied by h bar. So the final term evaluates to 2 h bar 2 plus 2. And I can repeat that procedure for any state to which L plus is applied. If we take another example, so if we apply L plus to the state 2 minus 1, we get again the complicated factor. L times L plus 1 would be 2 times 2 plus 1, minus the existing value of ml, which is minus 1, and multiplied by the value of ml plus 1, so the new value of ml, which has been raised by the raising operator. Well, when minus 1 is raised, we get 0. So we have this relationship here. Again, we can evaluate the terms. 2 times 2 plus 1 again evaluates to 6. The second term evaluates to 0 here. So we have actually h bar root 6 times 2, 0. And we can repeat that for all of the states in the L is 2 set of states. Let's just now try to do it for the state where we're already at the maximum value of ml. So for L equals 2, the maximum value of ml is 2. So what happens now when we try to raise the value of ml when it's already gone up as far as it can go? Well, let's just turn the machinery. We would get h bar times again L plus 1 minus the old value of ml, which is 2, times the new value of ml, which would have 2 raised to 3, square rooted, and then we'd get the state 2 plus 3, which actually is an illegal state, but we don't need to worry about that because this factor here, if we evaluate it, this is 2 times 3 is 6, and this is also 6. So these factors cancel out and I get 0, and the result of applying L plus to the state which already has ml as raised as far as it will go just generates 0. So the state self-destructs as it shifts off the top. And the same applies when we do the same calculation to L minus. Applied to the state with the lowest value of ml, then again the calculation gives 2 times 2 plus 1 for the first term, minus the value of ml, and the value of ml when it's been lowered by 1, so from -2 to -3. And again I would get the state 2 with -2 lowered to -3. This state is illegal, but don't worry, because again this term cancels out. We have 6 here, and we have -6, and again we get 0. So by shifting the lower state off the end with the L- operator, we again get 0, and everything works out happily. Now let's have a look at the matrix representations of these operators. So let's take, for example, case L is 1, and let's look at the matrix representation of the L plus operator. So running through the arguments we did before, it's going to be a 3 by 3 matrix, because there are 3 states with L is 1. And I can label the columns of the matrix using the kets. With L is 1, then we have 3 kets, and I have 3 bra states. And I can evaluate each element in turn. So if, for example, we take this element here in the bottom right corner, here we use the bra state 1 minus 1, we have the operator L plus, and the ket state, which in this case is also 1 minus 1. And I can run through the arguments where I apply the operator to the ket first. So this would give the complicated factor, in this case h bar, the L value times the L value plus 1, minus the existing value of ml, which is -1, multiplied by the existing value of ml raised by 1. So that would be -1 raised to 0. So that becomes 0, square rooted, and the new ket would be 1 with -1 raised to 0. Let's just evaluate the factor. The second term evaluates to 0. The first term evaluates to 2, square rooted, so the whole term evaluates to h bar root 2, 1, 0. And now I have to take the bracket with the bra state, which is 1 minus 1, so the whole term becomes h bar root 2, and now the bracket 1 minus 1 with 1, 0. But the orthogonality rule means that since these two states are different, the bracket between them is 0. So the matrix element of L plus in the bottom right hand corner simply evaluates to 0. Let's take a different term. Let's take, for example, this one here. In this case, the bra state is 1, 0, and the ket state is 1 minus 1 as it was before. So I can apply actually the same reasoning I've done for this state until I get to this term here. So this evaluates to 1, 0. That's the bra carried through, and then I have this numerical factor h bar root 2, and now the ket state, which has been raised, so that becomes 1, 0. And now I see that the bracket between the state and itself is just 1. So the term evaluates to h bar root 2. And in fact, if I continue that derivation, I can derive the 3 by 3 matrix for this L equals 1 case is given by h bar root 2 for 2 elements and zeros everywhere else. And notice that there are no elements of the matrix representation of the operator L plus along the diagonal, and the only elements which are not 0 are in a band which is displaced by 1 just above the diagonal. So this is called a band matrix, where the only elements are in a band parallel to the diagonal but not on the diagonal. And that's true for all values of L. I can go through identical arguments for the lowering operator to find the structure of that matrix as well, for the case L is 1. And again we have a 3 by 3 matrix, and again it's a band matrix where the only elements though are below the diagonal and all the other elements are 0. From these two matrices I can construct the two angular momentum matrices along the x and the y axes. So the Lx matrix is given by half the sum of L plus and L minus, which is given by half h bar, and now we just add the two matrices together element by element. And this time we have two bands, one above the diagonal and one below the diagonal. Similarly, the Ly matrix is given by the difference between the two matrices for the raising and lowering operator divided by 1 over 2i, and again evaluating that explicitly I get 1 over 2i h bar, a matrix with two bands, one above the diagonal and one with opposite sign below the diagonal. So those are the matrices for Lx and Ly for the case L equals 1. So now we have formed the matrices for the three angular momentum operators for the case L equals 1. Now a property of the angular momentum operators is the cyclic commutation relationships. These matrices have exactly the same properties. We can verify that. So for example, if we take the commutator of Lx and Ly, that's Lx times Ly minus Ly times Lx, and now we set to work and multiply the matrices out. So when we multiply Lx and Ly, we're going to get these factors multiplying, so I'll take those out straight away. Multiply those two factors together, we'd get h bar squared over 4i. And now we have a product of the two matrices. And we have to perform some matrix multiplications now. So here we multiply two matrices together and we should get a third matrix. And the way this works is the top left element of this new matrix is going to be given by multiplying the top row of that matrix by the left column of that matrix, in which we multiply the elements pairwise and add the result together. So that element in the top left is given by 0 times 0 plus root 2 times minus root 2 plus another 0 times 0. So the result there is minus 2. Similarly, the next element along is given by the top row of the matrix multiplied by the middle row of the second matrix. And here I have 0 times 0 plus root 2 times 0 is also 0 plus 0 times minus root 2, which is also 0. So I get 0. And if I repeat that process for all combinations of the elements, then I get a matrix which has the following form. If I now evaluate the second term, I get a matrix with a similar looking form. And when I evaluate that result, I get h bar squared over 4i multiplied by a matrix of the following form. So I've evaluated that matrix, the commutator of Lx and Ly, to give this expression here. And we expect it to give IH bar times LZ. So let's just see if we can convince ourselves that that's actually true. So let's just cancel out these minus 4s with a 4. If I take the minus 1 outside, I can write this as follows. We can see that the LZ matrix looks now similar. I have the 1, 0, minus 1 on the diagonal, just as it is here. And I can take an h bar outside. So I could write this as minus h bar over I times h bar. And we can see that this second part of this expression is the matrix representation of LZ. So I can write this as minus h bar over I LZ. Now whenever one has an expression in which I appears below the divide symbol, there's a trick one can always use, which is to multiply by I both above and below the line. I divided by I is just 1. So since I squared is minus 1, this evaluates to minus I h bar LZ divided by minus 1. The minus 1 and the 1 cancel out and I get, as expected, I h bar LZ, which proves the commutation property that Lx, Ly, the commutator, is given by I h bar LZ for these matrices for L equals 1. And this can be easily verified for matrices with L is 2, L is 3, and so on. Okay, next time we're going to proceed to look at the physical effects of angular momentum, including the Zeeman effect, and we'll introduce the topic of spin.